Good morning to all of you. Good morning, everyone. Very soon our speaker will also join. Rao sir, voice is clear.
Yes, sir. Yes, sir.
Very soon our speaker will also join from IIT Kanpur.
It's 11 o'clock.
Sir. Very soon our speaker will.
Hi, hello. I can. You are.
Good morning, sir.
Yeah. Good morning,
Good morning.
sir. You don't have to call me sir. Just call me Manjesh. It's fine.
Okay.
Sorry for the delay.
Yes, sir.
I'm sorry for the delay. Am I
No,
audible?
it's okay,
Or?
it's okay. You are on time. You are on time perfectly. You are on time.
Manjesh, I am also make a co-host to you. So if sometimes somebody unmute himself, then you can mute from your side also.
I don't know if I would be tracking that, but okay, you can do it.
You can also show your good-looking face also to all.
I'm sweating like anything. If you want, you can see me, but I'm sweating like anything. So that's why I don't want to.
Oh, always IIT Kanpur office is always good. So right now AC is not working there.
No, AC is working. I just came biking, so that's why I'm
Ah.
saying. So I just want to check once whether my simulations are.
Maybe you can share the screen and then you can check it.
Yeah. Tell me if you can see my presentation full screen.
Yeah, presentation you
Yes,
just
yes, sir.
on
Yes.
forward.
Okay, wait.
Yeah, it is working.
Okay.
If you want to check any video is there, then you can just see. Yeah, it is working video.
No, I
Simply.
don't have video. I normally don't keep videos, but that's fine. It looks fine.
Okay, no issue. It's working.
So I'll stop sharing for now.
Ah,
So, one thing. So how are things?
Fine, fine, sir. Fine.
As I said, you don't.
Thank you so much for taking time out of your busy schedule to join us today. Yeah, and to deliver your the wonderful talk.
Oh, it's wonderful.
So we will start, sir.
Yeah,
I'll give the brief introduction,
Yeah.
and we can start. Okay. So very good morning to everybody. We have our the first speaker on the day 2 of this 5-day international short-term course on tribology for sustainability. We have Dr. Manjesh Singh with us. So it is my honor and privilege to introduce Doctor to all of you, to all of us. So Dr. Manjesh K. Singh joined the Department of Mechanical Engineering, Indian Institute of Technology, Kanpur on 16th September 2019. So it's almost a year, sir. As an assistant professor, the principal areas of his research are tribology and rheology, mostly with the polymers. He has an interdisciplinary background with education in mechanical and materials engineering and a rich experience in both computer simulations and experiments. So it is indeed, it's a very unique expertise of the professor having the experience in both computer simulation, as we are going to see from his lecture today, as well as the experiment. Dr. Manjesh K. Singh is a life member of Tribology Society of India. The professional experience is, as I just mentioned, he joined in last year, September, as assistant professor in mechanical engineering department in IIT Kanpur. He was the postdoctoral researcher in the area of polymer tribology, MPIP mines from August 2016 to September 2019. So more than 3+ years. Then he was the postdoctoral researchers, LSST, ETH Zurich from February 2016 to July 2016. So for a short period of less than a year in Zurich. And Dr. Manjesh K. Singh was research assistant again in the same place, LSST ETH Zurich from 2011 September till January 2012. So it has been a fantastic professional experience. His education is, he has obtained a Doctor of Philosophy in 2016 in the Department of Materials, Swiss Federal Institute of Technology, ETH Zurich, Switzerland, and with the thesis titled Simulation and Experimental Studies of Polymer Brushes Under Shear. The supervisors are Professor Nicholas Dispenser and Professor Dr. Martin Kroger. So many of us have been fortunate, in fact, to listen to Professor Spencer, many of his inaugural lectures in India and abroad. So it is indeed great, sir, to know that you have actually gained your expertise in the area of tribology under the supervision of Professor Nicholas Dispenser. And Dr. Manjesh K. Singh has obtained his ME in 2011 from Materials Engineering, Indian Institute of Science, Bangalore, India, and BE, Bachelor of Engineering in 2009 from Mechanical Engineering, Indian Institute of Engineering, Science and Technology, IIEST, Shibpur, India. I think it was previously the Bengal Engineering College, where my supervisor also did his bachelor's. So it is indeed wonderful to read out your biodata, the short biodata. And with this, we are again, giving you a hearty welcome to join us on this day too. So the floor is yours, sir. The floor is yours. The platform is yours, sir. Thank you.
Thanks a lot. I'll just first switch off my video so that I don't get distracted.
Okay, sir. Okay. Okay.
And
Okay,
here my screen, let me know if things are visible, if it's everything is fine, or just a minute. Just a minute. Just a minute. Is my screen visible now?
Yes, sir. Yes, sir.
Okay, just a minute. I have to get rid of these things. Okay, so thanks a lot for the opportunity and a very nice introduction. Just I would like to mention that even though I've worked mostly with polymers in my PhD and postdoc, but most of the work or half of the work which I'll show you today is on nanoparticles or inorganic nanoparticles. There are no polymers there. And to add to your disappointment, I'm sorry, I will be not talking about any of my simulation works, even though I have done in my master's, PhD and postdoc, everywhere simulations, molecular simulation or FEM. But today I'll be talking about only my experiments and in general about aqueous lubrication. So with this, I would like to start today's talk. So I would start with the very topic of this short-term course. So normally, whenever we think of lubrication, we think of oil. I mean, we know roughly 1% of all mineral oil in the world are consumed for lubrication purposes, and this is primarily because it has very good technical properties, and it has, I mean, as always, it has reasonable price, and that makes it very attractive. But the problem is with this biodegradability of mineral oil, and which is very harmful for our environment, or and it increases the carbon footprint. So I mean, there are now, I mean, I know at least for last 1.5 decade or 2 decades, there are now people focusing like to get rid of oil as much as possible. and to make tribology more and more green. And the efforts are like basically directed with an objective to take care of health and safety of people in influence on equipments and buildings, and destructions or disposal of waste and remaining products, because that is also another big problem. Like we have, I'm in Kanpur and we have Ganges, and also we just simply throw away all this waste there, which is not biodegradable, and it causes harm to our environment, to the river and everything, to the ecosystem completely. So with this, I'll move to the next slide. As I said, the improvement efforts are primarily directed at the elimination of dangerous chemicals, so chemicals which are harmful, like chlorinated additives, phosphates with heavy metals, sludge, and all. Reduction of waste, including prolonging tool and lubricant life, recovery and reuse of lubricants, basically recycling, and then minimal quantity lubrications to avoid, we have to basically, the idea is to make optimum or put optimum quantity of lubricants required for the lubrication, no more or no extra, which will be like then disposed to the environment. And then like my topic is aqueous lubricant. So I just would like to highlight water as a lubricant, why we don't see water commonly used as lubricant. But like there are some properties of water which makes it potentially a very good candidate for lubrication. Like it's readily available, it's non-toxic, it's environment friendly, and it has high heat capacity, which gives it excellent heat transfer properties. At the same time, water has very low boiling point, and whenever you have frictions involved, you have very high heat generation, and then the low boiling point of water is a disadvantage. And the biggest disadvantage with water is this low high pressure viscosity index. Normally with all this oil lubrication, as you increase the pressure, the viscosity increases, which gives oil-based lubrication or lubricants this load carrying capacity, which water doesn't have. Now, if you have water in contact and you apply load, water will simply squeeze out because the viscosity doesn't increase as you increase the pressure. But still, there are some specific field where water is used as lubricant. One of the most prominent, which I would like to highlight, is this mining industry, because we want to avoid using oil as much as possible. We don't want to use oil inside the mines because there are very high chances of catching fires and all. So it's water which is primarily used for lubrication purpose there. Now, I told you the limitations, but there are some because the water has some attractive properties which we would like to exploit, but water on its own is not good for lubrication. That's why we have to add something to this, and then we have to exploit the good part of it. And for the drawbacks, we have to add something else. And there are two opportunities which I have explored during my master's and my PhD thesis. So the first one is this nanoparticles. So you have layered structured nanoparticles, which I'll come into detail later. And I'll talk about both these parts. I will have part 1 and part 2 of my talk. And second one is polymer brushes. All the lubrication in nature in our body is based on polymer brushes, and it's based primarily on this aqueous lubrication. With the help of water and polymer, we have lubrication. Polymer in the body means protein and all, glycoproteins and all. We have lubrication in body. So I'll talk about these two topics in a bit detail. So I'll first start with this nanoparticle-based aqueous lubrication. So the stock would have, I'll give because it's a short-term course. It's not just a technical presentation. I'll give you a brief introduction, a brief introduction to emulsions and emulsifiers. What are they? Oil in water emulsion, which is normally used in metalworking, and then objective approach, which I undertook during my master thesis. And then this why we want to use nanoparticles, then the experimental details, experiments which I did, the results, and then summary. And I'll summarize this part of talk and outlook. As I mentioned, I will not have any simulation parts in this presentation. So emulsion and emulsifier, I'll start with this. So introduction, why we want to use this nanoparticle-based aqueous lubrication or aqueous lubrication. As I mentioned before, this traditional lubricating oils have very low biodegradation rate. Water has some advantages which we want to exploit, and nanoparticles, because of their small sizes, can easily get into contact zone, and because of their layer structure. So we cannot use just any random nanoparticles. It has to be nanoparticles which have their certain materials which have layered structures which shear easily and gives us low coefficient of friction. So what is emulsion? First of all, emulsions are, or emulsion is a heterogeneous, or emulsions are a heterogeneous mixture of two or more immiscible phases, continuous and dispersed phase. For example, oil in water emulsions. Here you have this water making the continuous phase, this blue part of this picture, and there are oil droplets which are basically dispersed phase. So this is oil in water emulsions, which we normally use in all our metal working lubrications. Like if you do rolling and all, you'll see mostly this oil in water emulsion is used for lubrication, where oil is roughly close to 90 or more than 90% is water, and then less than, I think close to 5%, even less, is oil, and rest is all water. And I will tell you how it works when it comes to the lubrication. But and then what I want to do, or what idea of my master thesis was, that we wanted to replace this water with nanoparticles. Sorry, the oil with nanoparticles. The water will be as it is there. We wanted to replace it with nanoparticles which have layered structures. So basically, we wanted to get rid of any oil in the metal working lubrication. So then emulsifier or surfactants, why do we need it? So generally emulsions are very unstable due to difference in the density of the dispersed and continuous phases. So you have like water and oil, or nanoparticles and water, they have density difference. If you use large particles, so they will just sediment on the bottom of the surface. If you use very small particles, then because of this high surface area to volume ratio, and van der Waals attractions, they will come together and form clusters. So you will not have a very well dispersed emulsion. So what do we normally do to increase the stability? We aggressively agitate the emulsions using sonicator in case of oil in water emulsion to break the oil droplets in smaller size. And we also add surfactants or emulsifiers, as they are known. What is emulsifier? Emulsifiers normally have one water-loving polar head, which is also known as hydrophilic head, and then the other oil-loving non-polar tail, which is also known as hydrophobic tail. So basically, one water-loving part and one oil-loving part. And what happens when you put this such surfactants in your oil in water mixture? So this oil loving part will arrange itself in such a way that, or it will orient itself towards oil, and this water loving hydrophilic head will arrange itself towards the water phase, and then in this way you have a stabilized emulsion. So this way your water droplets will be stable in the continuous phase of water. Yes, oil droplets will be stable in continuous phase of water. So how, and as I said, I will explain how this oil in water emulsion works. So this is a simple example of oil in water emulsion lubrication in case of rolling. So what happens is that, like you can see this, I mean, they have used a different color, but this blue or green thing is basically water phase. This yellow ones are this oil droplets. And as you move in the contact, basically you can divide this part into 4 different parts: supply zone, concentration zone, pressurization zone, and contact zone. So as this emulsion is dragged into the contact zone, as I mentioned before, water has very low pressure viscosity index. The water will simply squeeze out, and you have finally to at the contact. It is just, I mean, as you move towards the contact, it changes from oil in water emulsion to water in oil emulsions, and when you reach the contact, you have only oil. So even in this case, it's only the oil which does the lubrication. What water does, because of its high capacity, it will take away all the heat generated. So the combination works very well. Oil takes care of the lubrication part, and water takes care of the coolant part. So this is the idea of this oil in water emulsion, or the mechanism. So what we wanted to do is to eliminate, as I mentioned before, to eliminate use of oil-based lubricant to improve carbon footprint, and to achieve the above goals by use of nanoparticle-based aqueous lubrication. And what we did is, like, as I mentioned before, water does not provide elastohydrodynamic lubrication, as water has a poor pressure viscosity index. It cannot support the rolling load. In case if you take rolling as an example, we suspend inorganic nanoparticles in water to provide load bearing capacity. So I'll now tell you a bit about nanoparticles. So the nanoparticles have several advantages in comparison to organic molecules, which makes it a potentially good candidate to be used as additive in the lubrication or in the lubricant. The nanometer size makes it possible for them to move into the contact zone without any difficulty. So just like what oil moves into the contact zone easily, these nanoparticles, because of the small size, they will move into the contact zone easily, and the water will be doing the same thing as it was doing in oil in water emulsion. It will simply transport these nanoparticles in the contact zone, as it was doing before with the oil. And these nanoparticles, because of their layered structure, they can shear easily, and that's why they will give lower friction. What I mean by this, so these are some of the typical examples of nanoparticles which are used as lubricant, normally used as solid lubricant, or many times used as solid lubricant. So all of this, like graphene or MOS2, WS2, or this HBN nano sheets, you will see they have layered structure. So within the layer, they have covalent bond, and between the layer, they have weak van der Waals interactions. So when you apply normal load, because of this covalent bond, they can support the normal load, but because of interlayer binding is very weak because of this van der Waals interaction, when you apply shear, they easily shear. That's why you have very low friction. So this is, I mean, how the idea was that we just replace oil with with these nanoparticles which can shear easily, and they will give us low friction or low coefficient of friction, so to say. So the experiments which we did, so I tried different nanoparticles, MOS2, Kaoline or Nanoclay nanoparticles. The surfactant which I used was sodium dodecyl sulfate, which is more commonly known as SDS. And these are the details of the concentration of particles and concentration of the which was used. Okay, I'll just continue. So what we did to prepare the mixture is that we sonicated it for 2 minutes using ultrasonic. So I didn't mix all the particles together, just one particle plus water, and one case just particle plus water, then one case one particle plus water plus the surfactant. Then we ultrasonicated for two minutes. Then we did the DLS experiment to get the particle size and zeta potential. And thereafter, we did ball on disk tribometer experiment at various speed and loads for different lubricants, I mean, nanoparticles suspended in water. And the material which was used in experiment was this bearing steel, EN31 of dia 6 mm, and disc, I mean, this was the ball, which in ball on disk tribometer experiments. And the disc is, was a stainless steel, SS304, which was used as a substrate for the experiment. So I'll move to the results. So first, DLS result just tells you about the particle size and zeta potential. So I'll not get into detail of these things. It just basically tells you whether they are finding, they are forming cluster, not like if you can see, for the example, kaolin plus water is very high size. You add SDS, the size decreases a bit, not much. So you can say that the suspension kind of improves, but if you look at zeta potential, it improves by a lot. I mean, higher zeta potential means more stable emulsion. And just water plus SDS, we also tried. I'll tell you why, the reason later why we did this particular experiment. So I'll not focus I mean, if you are interested, you can ask me later this from this part. So I'll just go into the tribological results or friction result. So first we started with the dry contact. So we had, so always on the left side, you have friction coefficient against speed at a constant load of 800 megapascal. When I say 800 megapascal, I basically have I've calculated this contact, Hertzian contact pressure, because I know the materials in contact and the geometry and all. So whenever I say the load in this part of this results or this part of talk, it's basically Hertzian contact pressure. So in dry contact and both speed and when we do it against load, at a constant speed, we see a pretty high friction value, which is like normal, which is expected when I did it in just pure water. Then also we get the similar friction. As we know, water cannot help us in reducing friction because it cannot support normal load. It will just squeeze out, and you have again metal contact or alloy contact or hard surface contact. Then we, just to be sure, we checked. As I said, if you do oil in water emulsions, it's basically the oil which takes care, which is taking care of the lubrication. So we just tested with oil what kind of coefficient of friction we get. Again, same speed and same load. So one experiment where we kept the load constant and we changed the speed, and the other one where we kept the speed constant and changed the load. We see the friction is like from 0.5, 0.6 or 0.65. We are getting down to all the way from 0.1 or 0.2 range. And then we just started with this nanoparticle in water suspension. So first is MOS2 plus water, this black one. So we see lower friction. When we add this surfactant, we see higher friction. I mean, but in case of when we plot it against contact pressure or against load, we see, I mean, the friction values are close, but the trend is a bit, I mean, there is a switch. So what we basically can say that when we add just nanoparticles to water, our friction already goes down to very low value, like what we got with the oil lubrication. So we are getting rid of oil and we are getting the same coefficient of friction. Then we repeated the same experiment with the nanoclay. In this case, nanoclay plus water was giving us very high friction. As soon as we added SDS, we got low friction. And okay, I think there's a switch. I think there's a color issue, perhaps, most likely. So that made us interested in what is the effect of SDS, or sodium dodecyl sulfate. What does it do? So to check that, we just did one experiment with just only sodium dodecyl sulfate and water, so surfactant and water, and we also saw very low friction. So I mean, if you look at, I'll go back to these results later again. So what we can say, in case of MOS2 plus water only, we are getting low friction. But with nanoclay plus water, we were not getting good friction or low friction. We were getting rather high friction. But when we added SDS plus water, we are getting low friction. So it could be that basically nanoclay is doing nothing. It's just the SDS which is forming a monolayer on the surface, and it is reducing the friction in case of nanoclay plus SDS mixture or suspension in water. We again repeated the same experiment with the kaolin plus water, and here also we saw this when we add SDS, we get lower friction. So I mean, we are not sure what is the role of SDS. I mean, the objective of adding a surfactant was to stabilize the emulsion. But what we saw, as in the previous slide, only SDS also gives us low friction. But in case of MOS2, we got low friction without the surfactant. So with this, I'll just compare the results. So what we can see, I mean, in all the cases, if you compare all the cases, so MOS2 plus water without any surfactant gives us low friction, even lower than water, even lower than oil. So it is a good candidate. I mean, the other two candidates, nanoclay and kaolin, didn't perform as good or as expected. But when we added the SDS, there also the performance is improving, but we are not sure exactly if it is because of kaolin or nanoclay or it is just because of SDS. But we can certainly conclude that MOS2 plus water gives us coefficient of friction which is comparable or even lower than with just oil for lubrication. So this could be one possible. I'm not saying that you should right away use it, but what I'm saying that we need to probe it further, but it seems to be a good candidate to replace oil in water emulsions for lubrication in metalworking. To summarize, as I said, the nanoparticle-based aqueous lubricants can bear high contact pressure of all the particles studied. MOS2-based aqueous lubrication gives the best results, and SDS in aqueous suspension alone also generates low friction. The reason for this behavior of SDS is not understood and requires further investigation. And this work I did in 2010-11 during my master's, and then after that I could never go back, because after that in my PhD and postdoc I was working with. So, or if you guys are interested, you are most welcome to look into these things in detail. So with this, I'll move to the next part of my talk, which is polymer-brush-based lubrication. So here again, I will talk only about my experimental work, no simulation works. So I'll take you to the introduction, what is polymer brush.
अभी भी एक चल रही है, अब क्या करो, जिसकी नहीं करो वो नाराज हो जाता है, लोग पर्सनल में भेजते।
Okay, so and then I will show you effect of different parameters. So this effect of cross-linking, I will show you the experiments which I did and results I will show you, and rest other parameters I'll just gloss over their effect on the tribology of polymer brushes. So introduction. So normally polymers or macromolecules, as they are known, they are basically large molecules made of repeating units, which we call as monomer. They are like synthetic polymers like polyethylene, polystyrene, all sorts of polymers all around. And then there are biopolymers like RNA, proteins. They are also, the physics of whether it is synthetic or this biopolymer is same. The chemistry is different, but the physics is same. As I said, we see it all around us. The reason is that polymers are very easy to process in complex shapes, and that's why it's being exploited too much as well, and it is becoming harmful to our advantage, and we're trying to limit its use in our day-to-day life as much as possible. So what is, whenever you talk about polymer, you'll hear these terms, good solvent or poor solvent. So what is good solvent or what is poor solvents? How do you make polymers? So you start with this red dot, which is like a monomer, and you start polymerization. So they form a polymer chain, this red one. And then if you are in a good solvent, what do you mean by good solvent? Good solvent for a polymer is a solvent which the polymer likes. So it would like itself to be surrounded by this with this solvent. So that's why it opens up and it is surrounded by the solvent, or the surface area or the contact surface area is with the solvent, or contact area with the solvent is more. But when you have a poor solvent, that means the solvent, the polymer doesn't like, or rather you can say hate, or maybe hate is a too strong word, doesn't like the solvent, so it will avoid any contact with the solvent as much as possible. So it will collapse like in a form of sphere or a globule to minimize its contact with the solvent. So whenever you say a poor solvent, you'll basically see the polymers are like collapse. And how you see, physically, if you want to check, you have a polymer, you want to check whether solvent is a good solvent or bad solvent for a polymer. You just add the polymer to the solvent. If you can see through, if the mixture is still transparent, that means it's a good solvent because the polymer is happily opened up. But if it's a bad solvent, they will collapse and you will see turbidity. So the mixture will not be transparent. So you can, at once you can say that it's a poor solvent for that particular polymers. Why I told you this, because I will be using this term good solvent or poor solvent in my talk today. So what is polymer brushes? So if you have polymers in a good solvent and you attach or you graft it or you fix its one end in such a way that the distance between two neighboring chains or grafting site is much higher than the radius of gyration of the individual chain, they'll form a mushroom-like structure. If you move them closer and the distance between the grafting site is of order of radius of gyration of the chain, they will be like semi-traced. If you bring them further closer, so that the distance between two neighboring sites is much lower than radius of gyration of the chain, they'll stretch out to form like a brush like structure because of entropic and excluded volume effect, and they will form a brush-like structure, which we call polymer brush normally. If you repeat the same sequence in a poor solvent, when you are far apart, you will form a pancake-like structure. If you bring them closer, they will form kind of a cluster. And if you bring them further closer, so they'll form a homogeneous layer on the surface. They will not stretch out in a poor solvent or in a bad solvent. I mean, bad means poor solvent, to form a brush-like structure. So there are primarily two methods to prepare polymer brushes. One is grafting 2, where you have polymer chains already in a solution. You pour it on the surface like we used to do on the silica surface. You pour it on the surface, and because of electrostatic interaction, it will get attached from the functionalized group. It will get attached to the surface and it will form a brush-like structure. The advantage here is the self-healing effect. Suppose you are rubbing your polymer grafted surface against something, and some polymer chains wear out. But then what will happen in grafting, if you have prepared your polymer brush using grafting 2 approach, what will happen, there's other polymers which are in the solution freely roaming around, they will come and replace it. So it will have a self-healing effect. But the limitation or the disadvantage is that you cannot achieve a very high grafting density here, because what happens is, suppose these polymer chains are occupying already some spot, then it will not let other polymer chains enter in between. So the grafting, you cannot achieve a very high grafting density with this approach. And the other approach is grafting from, where you first attach the initiator to the surface and then you grow polymer chains out of it. Here you will get very high grafting density, but you don't have self-healing effect. So both the approaches have their own advantages. So what is the application? What is the application of polymer brushes in field? So like use Tribology that I was talking about surfactant. So you can also think of when you attach your colloidal particles with or you grow polymer brushes on your colloidal particles. So as the chains would like to avoid each other, the particles will be happily suspended in the solution. The other is biocompatibility. You want to avoid protein, or any bacteria getting attached to the surface. So infection-resistant surfaces, and I have seen during this COVID time, many people are kind of using this polymer grafting on the surface and then claiming that this mask or that mask or this fabric will antibacterial or anti-infectious. So then you have adhesion as well. If you want to avoid adhesion from a surface to a surface of another surface, people attach or grow polymer brushes on the surface, and this way you don't see adhesion, or you avoid adhesion. So you can control adhesion between two interacting surfaces. The other part where I will focus, or my work is, so as I was saying, that all the lubrication in the nature is based on this polymer brush in our joints, in all the joints, or in any living thing. This lubrication is basically based on polymer brushes. And how it happens is, just to give you a simple example. So you have these surfaces and you have these glycoproteins which are attached to the surface. And as I said, they form kind of polymer brush-like structure. And then you have this synovium or synovial fluid, which they say. I am not very used to this biological terms. So synovial fluid, which is in between, more like kind of water, something like water or any solvent, which the polymer, in this case glycoprotein, likes, will be in between. And these polymers will take care of load carrying capacity, and this solvent in between, because of its low viscosity, will give you lower friction. So explain you in detail. So what happens is, like, I have not shown you the solvent here, because if I put the solvent particles, you will not be able to see the polymer. So here I was, as I said, I was doing simulations in my PhD as well. So what happens is that your polymer chains grafted on the surface, because of excluded volume effect or entropic reasons, they don't want to interdigitate. So if you look at the density profile, you will see that this gray and yellow color curves are for the polymer or monomer density. As you move away from the grafting surface, their density is going down. But at the same time, if you look at the solvent particle density, which is not shown here in the snapshot or in the animation, their density goes up. So what exactly happens is that polymer brushes, because of strong interchange repulsive force, prevent interdigitation, and the thin fluid film or kind of support the normal load, and thin fluid film between opposing brushes or brush and counter surface. So there's this thin film of fluid or liquid in between, which is formed, which takes care of lubrication, or it assists in reducing the friction at the interface. So this way, if you have a hydrophilic polymer for which water is a good solvent, and you use water with this polymer, so this polymers will take care of the load carrying capacity, and this water, because of its very low viscosity, will reduce the friction. I mean, if you have brush against brush system, the friction will be too low that you cannot measure with the experiment, most of the experiment tools which are available today. So something about polymer brush tribology. So we normally know this famous Tribeck curve, that it has a boundary lubrication where you have contact between the mating surfaces. Then you have mixed lubrication where you have some part where there's contact, some part where you have fluid film in between, and then you have hydrodynamic lubrication where there's always a fluid film in between, and there's no hard surface contact, or there's no contact between the mating surfaces. But if you look at this polymer brush-based lubrication, you have, these are my simulation results, these are experimental results from one of my colleagues. So what you see that you have hydrodynamic lubrication regime, you have mixed lubrication, you have boundary lubrication or boundary-like regime, but you don't have any mixed lubrication. So you just go from boundary to hydrodynamic. You don't have any mixed lubrication regime in between, and which makes it very interesting as well. This is just to give you an information. If you are interested, you can read more about it. So I will now show you effect of cross-linking. What happens if you increase the cross-linking to the tribological behavior of polymer brushes? So what do I mean by cross-linking? So as I told you that we grow polymers out of surface, and then we have polymer brushes. So we can also do that. We can cross-link this chain. The reason why people normally do, or we would like to cross-link the polymers, is to increase the modulus. Normally the polymer and solvent only will have very low modulus, but so they will wear off easily. But if you do the cross-linking, you can improve the modulus or stiffness, and so you can reduce the wear. So you have to have a combination or you have to have like kind of brush and gel, and you have to have optimum cross-linking so that you have low friction and low wear as well. Because if you have a lot of cross-linking, as we will see, the friction will go up. So here also there are two methods to create this cross-link polymer brushes, or as they are known as polymer gels. One is initiator modified substrate, so which we also call it in situ method, where while you're growing the polymer chains out of this initiator, you cross-link them. The other one is post-processing, or we call it ex situ, where you first grow the polymer chains. You have functionalized monomers or ends in the chain, which after you grow the polymer brushes, you functionalize, or you get them react to form the polymer gels. So in my experiment, which I am showing you today, the polymer gels were prepared using the second method, or we call it ex situ method. But I would like to tell you that I am not a chemist, so I didn't do this part. I did the testing with AFM and all, and I did the simulations, but I am not an expert to prepare this polymer brushes or gels, because I'm not a chemist and not good with chemistry as well, so to say. So what was the objective of this study? To model, model, but I'm not showing you, to model the polymer brushes using coarse-grained molecular dynamics technique to characterize the tribological behavior of various polymer brush systems using colloidal probe-based lateral force microscopy, which I will tell you what do I mean by this, and to elucidate how, or to give you the molecular design of brush system. If you want to have a certain kind of lubrication, what parameters you need to control and how much you need to control. So basically it's giving you a design rule for designing polymer brushes with the optimum or required required lubrication properties. And we do it by like feedback loop between experiments and simulation. But here I will show you only the experimental part of my work. So the material first. So what we had was PGMA, this polyglycidyl methacrylate brushes and gels. The solvent which we used was DMF. So of course, it's a good solvent for PGMA brushes and gels. And then we have used two kinds of cross-linkers. The other was is short, which I call it C2. And then we change the degree of cross-linking for each of the cases to see the effect of degree of cross-linking. So as I was saying, we use AFM-based colloidal probe lateral force microscopy. So normally we know that we use AFM to get the topology of the surface by tapping mode or different mode, because when you take it on, you do the rastering of the surface, you will because of the surface profile, your cantilever will move up and down, and you can get the profile of the surface. But you can also measure the friction using AFM. What you do is you have four diode quadrants. So when you apply lateral motion to your cantilever, and I mean whenever the cantilever, or of course the cantilever will face the lateral force, so it will twist and it will move on the diode in XY direction. And from there, if you calibrate your cantilever in the lateral direction as well for lateral stiffness and sensitivity, you can measure the lateral force or friction force, so to say. You know what force you're applying because you know what voltage you applied. So you know the normal force, you know the friction force, and you can get the coefficient of friction from there. So as I said, we use colloidal probe lateral force microscopy. So I didn't use the sharp tip, cantilever with sharp tip, because we are using polymers in our experiment. If you go with a very sharp tip of silicon carbide or something, it will simply scratch off your polymers. So you will not get to study what you want to see. So what we do, we bought tipless cantilevers. We attached colloidal sphere, the silica colloidal spheres on this tipless cantilever. What it does, that now we don't have a very sharp tip, and we have a well-defined geometry. We have a sphere, so we have a well-defined geometry. We have a higher contact area because we are using a sphere. So the contact pressure goes down, and we have a well-defined geometry. So it will also help us to, if you want to deduct the contact pressure or contact mechanics there, it will, you can do it because you have a well-controlled geometry, or the geometry which you know. And what you do in AFM, normally you have a trace and a retrace curve, and then you take average of these two curves, and then from there you get the friction force. So this is trace curve, this is retrace curve. You do this minus this divided by 2, and you have your I mean, you can take, if you want to take average, you can take the modulus value of each of this, or you can just simply subtract one from other and divide it by 2. You will have a friction force. You have applied the normal force or voltage. You know the sensitivity and the stiffness, so you know normal force, you know the friction force, so you can get the coefficient of friction. So the result, so here are my results. So first one, you will see red one is the bare silica. When I did silica sphere against bare silica surface, there is no polymer brush, no polymer gels, we got a friction. I mean, there's a linear curve of friction force against normal load, which we expect. As soon as we grafted polymer chains, so P equal to 0 means 0 degree, or means no cross-linkers are there, it's just polymer brush, you will see the friction force goes down by order of magnitude. So I mean, at the same normal load, you have very, very low friction force. So as I said, polymer brushes help you to reduce the friction. So, and then as we increase the degree of cross-linking, we see higher and higher friction force. And if you take the slope, you will get the coefficient of friction, and you can safely say from here that as you increase the degree of cross-linking, your friction force or coefficient of friction goes up. So this is for C2 cross-linkers. And we also did this AFM-based nano indentation curve, again with the colloidal sphere attached to the tipless cantilever. And here, what I show you, I mean, people use it to get the modulus as well, which I would like to avoid, because I would not like to believe AFM data in terms of to tell me the exact measurement or magnitude of the modulus, because we don't know exactly the contact point and the other complications involved this. But what it can tell you for sure which one is softer and which one is stiffer. So how I can tell you this? So this change in slope, which you say, which you can see on your screen, is basically tells you that the polymer is already filling the substrate. So this sudden change in slope indicates the change, indicates you that the polymer, the silica sphere fills the silica or silicon wafers or substrate on the surface. So what it tells you that as you increase the degree of cross-linking, your swelling of the polymer gels is going down. That's why it can feel the substrate very early. And when you have very, or you have no cross-linking or very low cross-linking, it feels the substrate very, at a later depth. So what it basically tells you that as you increase the degree of cross-linking, your swelling in the polymer gels or polymers goes down. And that's why your lubrication, as I said, if you increase the degree of cross-linking, you have no free polymer chains at the outer end. So your lubrication behavior will go to worse. But I mean, there are studies which shows that it will improve your wear property. So you don't want a very high friction and low wear, or very low friction and high wear. So you want an optimum in between. Again, we repeated the same experiment for C6, longer the longer cross-linkers, and we have the similar trend here as well. And I'll just quickly move to the coefficient of friction part. So this is, I mean, I have shown here only the simulation results. I've not told you the simulation details, what all I did there. So what we can tell clearly from here is that as you increase the degree of cross-linker, your coefficient of friction goes up, both in simulation and experiments. But as you increase the length of cross-linker, your coefficient of friction is going down. In simulation, it was very clear and it was consistent. But in case of experiments, the effect of length of cross-linker towards the lower degree of cross-linking is not very clear. And don't compare these numbers of coefficient of friction on both sides, because we are not, and the idea was not to make a quantitative comparison, because I was doing the simulation in a reduced unit. So it was not all atom simulation, or it was more of physics side. So we are basically comparing the qualitative or the trends which we see in simulation and experiments. With this, I'll move to the effect of grafting density. I think my time is also closing. So effect of grafting density. So as I said, there are different parameters which will affect the polymer-brush-based lubrication. So if you have very low grafting density, again, these polymers, there are less polymers to support normal load. So the solvent will squeeze out. If you have high grafting density, they can support the normal load, and the solvent in between then can help you to reduce the friction. So as expected, if you increase the grafting density, the coefficient of friction will gradually go down. Then we will move to effect of chain stiffness. So what do I mean by chain stiffness? So these are, I mean, we normally in simulations, I can just tell you this, take this KB as bending rigidity or bending coefficient. So as you increase the bending coefficient, you can see the polymer chains are more and more stiff or stiffer. So this is what I mean by chain stiffness. So here also we saw that as we increase the chain stiffness, then there's no effect on the normal stress, but the shear stress is decreasing as we increase the stiffness. So here also, I mean, I can say, if you want, we can discuss it later in detail. Basically what happens is that as you increase the chain stiffness, your friction goes down. Then effect of solvent. Polymers, as I said, have this good solvent, bad solvent. That polymer is very interesting material. It has also have something called co-solvency. What is co-solvency? Suppose there are two solvents which are individually a bad solvent. Each of them are bad solvent for the polymer. But when you mix them at certain mixing ratio, they will behave like as if together they are a good solvent. So we call it co-solvency. Then there's a co-non-solvency behavior as well for polymer, where two good solvents for polymers, which are individually, each of them are good solvent for the polymer, but when you mix them together at a certain mixing ratio, they will behave as if they're the bad solvent for the polymer, and the polymer will collapse and will not form a brush-like structure. So we can exploit it to design smart lubricants. So what do I mean by when I say collapse or swollen? So these are like I mean, the top one is like what we call co-solvencies. On the both side, you have poor solvent. So that's why this curve actually is basically, I mean, it tells you you can say kind of the swelling or the size of or the thickness of polymer brushes as you have both side pure bad solvent, you have collapsed state, but as you mix them at certain ratio, they swell and they form brush-like structure. Same thing goes about non-solvency on its own. I mean, both side they are like the polymer brushes are like in a swelled state, so they help in lubrication. But at somewhere in between, they are in collapse state, so they don't form brush-like structure, and you will have lower friction. And people have studied this, so you can have like water ethanol mixture like for Pinay pump, and people have studied this. So when pure water, you have polymers which are stretched out and they're forming brush-like structure. Pure ethanol also, they are forming brush-like structure, so you will have low friction. But at 30% mixture, they're in a collapse state, so you'll have higher friction, which you can see from this force and separation curve. So at 30%, you will see this trace and retrace curve gap is very high, which basically tells you that there's high friction force. But in pure water and pure ethanol, this trace retrace curve is quite close, so you have basically low friction. With this, I'll move to effect of chain length, which is, I mean, something which is not very clear. So here again, these are my experiments. Bare silica gives you very high friction. As soon as you graft polymer chains on the surfaces, the friction goes down. But there are two curves. I mean, in this plot on the left side, you cannot see it, but on the right side, you can see when I zoom it. I mean, we don't have any clear understanding what happens with the length of crosslinker. So initially, chain with with the length of polymer chains, not crosslinkers. We don't have crosslinkers there. So with the length of polymer chains, so initially we see that lower chain length gives higher friction, then there's the higher one which gives lower. So this, I mean, something which I don't understand, and I mean, what I know that nobody understands, or there's something which is not studied theoretically yet. So we don't know this part. We repeated this experiment with another colloidal probe of polyethylene. Still, we don't have any consistent results. So what I would like to basically say that effect of chain length is still not understood. So if you're interested, you can research in this direction. I mean, you can have a project or you can work on this in this direction. It's an open problem, and then there are like brush and gel structure. As I was saying, that the gels are basically they're stiffer or higher modulus, so it gives you lower wear, but simply polymer brushes gives you lower friction. So you can have good of both the world, or better of both the world. So you can have gels on the bottom and brushes on the top. So you will have lesser wear, and because in the top layer you have brushes, you have lower friction. And these are my simulation results again. So what you can see that when I have gel over, the red one is only brush, the blue one is when gel is on top of brush, and the green one is when brush is on top of gel. So what we see is that when gel is on top of brush, we have higher friction, but when gel is over, when brush is over gel, the friction is same as if there is no gel. I mean, just only polymer brushes. I'm sorry, I have to move it quickly because I think my time is closing. So I mean, just to tell you in short that if you have brush on top of gel, it will give you lower friction and it will improve perhaps the wear behavior as well, but I have not studied the wear properties. With this, I'll just summarize that tribological behavior of polymer brush can be tuned by controlling different parameters. It can be concluded that thickness of polymer brushes is the most important factor in deciding the frictional behavior. Polymer brushes can be designed to achieve specific tribological properties for application in biotribology, and mostly in the transplants and all, we have this kind of lubrication, or in contact lenses. Contact lens is the perfect example of polymer gel-based lubrication. Your contact lens is nothing but a polymer gel. Then polymer-based lubrication has been shown to be working in the range of hundreds of megapascal. So people are studying if we can use this kind of lubrication, suppose with water, with a hydrophilic polymer, we can use it in the metalworking and all, and we can get rid of any oil in our system. and then synthesizing stratified layers of brush gel or gel brush structure by controlling cross-linking can lead to of specific mechanical and tribological behavior. I'm sorry for overshooting my time. And there's still a lot of research study required to use polymer brushes for lubrication in different industries. Role of entanglements among grafted polymer chain is still not well understood and needs further studies. This is something which I'm planning to do now with an IIT Kanpur. With this, I'll summarize. If you're interested in second part of talk in more details, you can go to this book. I think where our Professor Katiyar is one of the editor, if I'm not wrong. I mean, not wrong. He's there. I'm sorry. I'm not wrong. He's there. And I have a chapter there in Polymer-Brush-Based Tribology. You can have a look there. With this, I'll thank you all. And if you have any question, I'm happy to answer. Anybody?
Thank you, sir.
Okay.
Thank you, Manjesh.
Yeah, just a minute.
Yeah, we have several questions.
Okay, so if you can ask me, then I'll try to answer.
So actually, one question asked by the Pawan Soni.
Yeah.
He wants to ask you about, as normal load increases, coefficient of friction should increase, but here it is reducing. In your case?
Where, in which case?
In first part of your presentation, you have shown that when we increasing the load, then coefficient of friction reducing, but he think that some different way. When we increasing the load, coefficient of friction will increase. Then what is the basic reason to decrease the coefficient of friction?
Why you think that increasing coefficient of increasing load will always lead in increase in coefficient of or increase in friction? I'll tell you why. Just give me 1 minute. So I will go to the Strybeck curve. Okay, where's my Strybeck curve? Okay, here it is. So I will share my screen as well, so I can explain it better.
My question is also related to this, sir.
Yeah.
If coefficient of friction is reducing, then how much its limiting value? That means how much number of load increases, after that it will increase again.
So I mean, so if you are saying how much load it will, we have to increase, that part I don't know, but
what will be your limiting load? Is there any limiting load? No?
There will be a limiting load, but what I mean to say is that I mean, so if you can see my screen, so I have this Strybeck curve. Okay.
Yeah.
Strybeck curve is speed into viscosity by load. Okay. So if you are if you're moving from boundary regime to the mixed lubrication regime, if you increase the load, you keep speed and viscosity constant. And if you increase the load from the boundary regime, so you move into the mixed lubrication regime, where when you increase the load, as the Sommerfeld numbers, sorry.
But there is not numerical value, no, sir.
What numerical? I mean, so this is
you have not discussed about what will be the value of load.
Actually, in this case, Anand, is the load is very means these polymer brushes is not applicable for higher load. So these are the load for very low load applications, and those are like disk and this hard disk and other devices. These type of the lubrication will be applicable.
No, but I think the question was from the first part, and you're asking me if I don't have number on my Strybeck curve, right?
Okay.
Okay, no issue. Next question is the Manjesh. Next question asked by the Nitish Prasad. Yes. He wants to know, does the synovial fluid must be modeled as a polymer brushes, as you said? No. It won't have mixed lubrication.
No, synovial fluid is not polymer. The glycoprotein is polymer. Synovial fluid is a solvent for the polymer or the glycoprotein.
Can biolubricant be modeled as the polymer brushes?
Yeah, I mean, that's what we are. That's what I was showing. The biolubrication or lubrication in our body is basically based on this polymer brush kind of lubrication. I mean, it of course has more complicated chemistry there. Could be. What I showed you is more simplified system, but yeah, it is the biolubrication or what we have, or in our joints and cartilage and all is basically polymer brush and gel based lubrication, where you have no synthetic polymer, you have this glycoproteins which are biopolymers, and you have fluid like synovial fluid or any other fluid which is good solvent for that particular polymer or for that protein.
Okay, next question from the Jaswant Hirwani. He wants to know why SDS affect increase friction in case of MOS2.
Why SDS? Okay, let me go back to that slide.
Affect increase in case of MOS2 means SDS increases the friction in case of MOS2, which
So,
you have shown
yeah, so
one slide.
yeah, so what could be, I mean, as I told, this study was done during my master thesis, which is some 2010-11, so some 9-10 years back. So I can give you the possible explanation is that MOS2 plus water was already giving us low friction. We didn't need SDS, but just to check, we added SDS, and we believe that whenever we add SDS itself forms a monolayer on the surface, and it doesn't let MOS2 to do the lubrication. So I mean, it could be a possible explanation because I have not studied it in detail. So the possible explanation could be that when you see MOS2 plus SDS plus water, the friction is taken, the friction part is taken, or lubrication part is taken care of by SDS and not by MOS2. But where in case of MOS2 plus water, it is MOS2 which is taking care of friction, and that's why we see lower friction there. And here we see effect of SDS and no effect of MOS2. Does it answer the question?
Okay.
Sir, one question from my side.
Yeah.
Is there any application of synovial brush in human body?
No, sir. Polymer brushes. Polymer brushes in human body is all polymer brush and gel on the human body or any living.
Where is the, sir, lab examples? Can you explain the current examples where it is used more nowadays?
I mean, you are saying, are you saying in our body?
Actually, you want to ask about any live applications of these polymer brushes in human body?
Yeah.
Either
in our joints, in cartilage, in any joint, we have this kind of lubrication. When we do any transplantation, suppose in hip transplantation or anything, we have this kind of lubrication that we put artificially. But naturally, in our body, in all our.
Have you any study about the side effect of these brushes?
I mean, no, I have not studied. The people who have studied, I mean, those who are doing biotribology.
Because any foreign particle not accepting our immune system, it will be side effect. Must be side effect. Okay. But so have you any idea about what will be the side effect and how much duration it will work?
But we have transplantation. Why are you saying that any foreign particle or foreign materials will have bad effect? We know that we have all sorts of transplantation in our body. I mean,
yeah, there will be the side effect. No? If you put anything from the external from your body, this will be the side effect. Either the hip joints, either the knee joint, this will not be continuous.
It will not be continuous because whenever you put these things, you normally coat this material which you want to put in your body with some polymers, which is essentially kind of a protein, and that will prevent. As I showed you, one of the example of polymer brushes is that it prevents absorption of protein. It will not let the proteins or other antibodies from your body to attack it. Okay, when your polymer brushes on the surfaces which are coated in the transplantation will wear out over a period of time, like in 15, 20 years or 10 years, whatever, this is the quality of your transplantation, then you will have this effect. And that's why you will see, not in India, but in West, especially in US or in Europe, you will hear many times this old people are suing the company, transplantation providing company, because now people are living for very long time. You had transplantation in 60, 65, and you are now 85, 90 years, and they are weird off. And now you are getting all sorts of trouble. So that's why now people are trying to improve the durability of such coatings. So
okay.
It's not as you just put the metal in there. You have some coatings always. So there are a lot of surface chemistry which goes. Yeah.
Another question from the Srinivas. He wants to ask you, can we consider SDS as a non-toxic?
I mean, sodium dodecyl sulfate. Sulfate, I don't think I will consider non-toxic exactly. But I mean, I'm not that much into chemistry, but sulfate I will not consider as such non-toxic. But as I showed in my whatever presentation, I mean in my presentation, just MOS2 plus water without any SDS gives us very low friction, even less than what we have with oil. So I mean, we don't have to worry about SDS there because we're not using.
Yeah, I think so also. And another question, I think Siva C, he wants to know, is any relation between zeta potential of the particles of the friction?
Yeah, if you have high zeta potential, I mean, normally what I would expect that if you have high zeta potential, you have more stable emulsions, especially, I mean, what I've showed you now today in case of particles in water, it is, I mean, I did it 10 years back. Thereafter, there are a lot of studies, so I have not looked into that. But normally when you have higher zeta potential, you have, it means your particles are well dispersed in the system. So you will expect lower friction, which is very, very true in case of oil in water emulsions. If you have higher zeta potential, that means more stable oil in water emulsion, and that means lower friction.
Another question, he also wants to know what the dimension of MOS2 used.
What was the dimension of MOS2 used?
I mean, what is the size of your MOS2 particle?
Yeah, that I understand, but I cannot tell you the exact number because I don't remember from 10 years.
I think so. Maybe that is in nanometer range. I hope.
Nanometer range is for sure, but whether it's, I mean, I think if I remember, it was something around 60 to 80 nanometer range.
Good afternoon, sir. May I just ask? This is Anish Singh. I'm a fourth. Thank you for this valuable session, sir. So my question is, can we apply polymer brush lubrication to surfaces which facilitate chip flow in machining, like flutes, rake surfaces?
No, that's what I said, that now, I mean, polymer brush-based lubrication has been mostly, like in our body and all, is used for soft surface lubrication. Okay, so now people, I'm in the group where I was for my PhD in Professor Spencer's group, there's one attempt, but somebody tried to do it on the steel surface. So, I mean, there she was not very successful, but there are some other studies, as I told towards my conclusion, that people have reached hundreds of megapascal of load, which is the kind of load, I mean, 600 or 800 megapascal, the kind of load which you have in metal working, or I don't know, in chip cutting and all. So,
yes, sir.
It can be used, but it is still not there. I mean, we are still, I don't know anywhere people you are using it. It is still mostly used for soft surface lubrication, but it's true that people are studying it. Okay, so
thank you, sir.
That's what I can say about this.
Yeah, and last question. This is the last question, Manjesh. Srinivas again asked one question: will the water and MOS2 mix from stable emulsion without addition of SDS?
So that's what we saw. I mean, I don't know about how stable it is, because from zeta potential it was looking quite stable. It was like the numbers were close with or without SDS, but the friction wise it was much better without SDS. So I mean, that's from my study.
Okay.
Can be because mine was only for 1 year.
I think without addition of SDS, it will also maybe stable for 24 hours, 48 hours, like that. Maybe not for 1 month.
I have used only one particular surfactant because of limitation of time and all, and I had another FEM simulation to take care of there during my master thesis. Half of the part was FEM simulation of cold rolling process, but there are other surfactants like CTAB and other things. So we have studied only one particular surfactant. So we can explore other surfactant and see how it affects the friction behavior. But in my study, I focused with, I did with only one surfactant. But based on that, what I can say that MOS2 plus water was stable and it was giving lower friction than MOS2 plus water plus the SDS.
Okay, thank you very much, Manjesh, for
Again,
such a nice presentation. Everybody appreciated your presentation.
thanks
It
a lot.
was good. And now next speaker is also, I think, waiting for
Okay.
next talk from the Indonesia. If
Okay.
you are free, please join that talk also.
I will try, but I have a meeting again to catch up. So just rush out.
Okay, okay, nice.
Thanks a lot.
Okay, thank you. इनको को होस्ट बना के आता हूँ मैं पहले पढ़िए सर Yeah, good afternoon, sir. Good afternoon.
Prof. Rao. Good afternoon.
How are you?
Can you
Thank you, sir.
hear
How are
me?
you?
Can you hear my
Yes,
voice?
yes, sir.
Okay.
Yes, sir, yes, sir.
Good.
You can also please share your slide, sir.
Okay. Please wait a moment. Okay. Is it okay?
Yes, sir, yes, sir, yes, sir.
Yeah. Okay.
Okay, okay, sir. So, welcome, everybody. So, it is indeed our great pleasure and honor to welcome our next speaker of day 2, Dr. Ziarul Faudi from Kaoline University, Indonesia. Yeah. So I'm indeed pleased to read out a brief bio of Professor. I'm indeed pleased to read out the brief bio of Professor. Professor Dr. Ziarul Faudi is in the Department of Mechanical and Industrial Engineering. Kaoline University, Indonesia. He did his bachelor's in 1996 from Universitas Kaoline, Master of Science in 2004 in Mechanical Engineering, University Science Malaysia, and PhD in 2009 in the area of Mechanical Systems and Design from Tohoku University, Japan. So in the PhD thesis title is Generating Mechanism of Low Frequency Stick Slip Motion and Creep Grown Map in the area of Mechanical Engineering. He has been lecturer in the University of Kaoline from 1996 to 2000. Then he moved on to pursue his research. He was research assistant in Tohoku University from 2009 to 2012. He was lecturer in University of Kaoline 2012 to 2016, and he's associate professor in University of Siakola from 2016 to till present. The research contributions and highlights are friction, tribology of palm-methyl ester, mechanical properties of single abaca fiber and composite, research on vegetable-based hydraulic oil with nanocarbon. The ongoing research activities are in the area of incorporation of nanocarbon allotrope in vegetable oil for hydraulic application. He is supervising a list of doctoral research students. Muhammad in the title heat transfer of asphalt hot mix during transport. Another student Sabri on the title effect of loading rate on mechanical properties of single abaca fiber. Muhammad Tajuddin axial flux motor for marine energy generator. I know it's great, sir, indeed, to say that the content, the topics of the doctoral students are indeed quite wide. So it is really glad to see your area of expertise in supervision in the wide range of topics. Professor Dr. Zarul is in coordination with the university's professor in the public funded and research projects from Tohoku University. So he's actually collaborating with Professor Koshi Adachi in Tohoku University, as well as Professor Toshiyuki Takagi in Tohoku University. So he's having the international research collaborations with these professors in Tohoku University. And Dr. Zarul has got a long list of funded projects. Way back in, he has secured a Taiho Tribology Research Foundation on the project design of contact interface for super low friction of carbon-based coatings under palm-methyl ester. Completed the project in 2013. Dr. Zarul Fraudi also secured a grant in the title effect of palm-methyl ester of friction and wear of carbon-based coatings during 2014 to 2016 $50,000 from the Department of Higher Education in the Republic of Indonesia. Dr. Zarul Faudi also secured an international institute fund from the Tohoku University in the area of study on fracture mechanism of single abaca fiber, completed last year for a duration from 2018 to 2019 for $15,000. Dr. Zarul also secured a project which is currently ongoing for $50,000 from the Department of Higher Education, Republic of Indonesia. The title of the project is Incorporation of Nanocarbon Allotrope as Nano Additive for Renewable-Based Hydraulic Oil. So, and of course, he has got a long list of publications in lubrication science, tribology letters, IMAQ Journal of Engineering Tribology, and so on. So his area of expertise is tribology and friction. And professional honors include, he is currently the Vice President for Indonesia in the Executive Committee, that is the Asia Tribology Council, ATC Executive Committee. He's currently the Vice President from Indonesia. And he has been in tribology, actively working in the field of tribology for more than 15 years. So, and he's actually looking forward to the development of research in the renewable-based hydraulic oils using nanocarbon allotropes as additives. So, Professor Zarul, it has been indeed really motivating to see your long biodata with a vast number of publications and projects, and of course the supervision and indeed international collaborations with Tohoku University with the Professor and his colleagues. So with a brief introduction, so I welcome you once again, and now the platform is yours, sir. Please.
Thank you, Prof. Rao, for inviting me for this international short course. Before starting, I would like to ask if my voice can be heard.
Yes, sir. Yes, sir. Very clear,
all of
sir.
you?
Very
okay.
Clear.
Okay. If there is some maybe internet connection maybe disconnected, please tell me. Okay. thank you for everyone. Good afternoon. Thank you for attending this session. So my talk, I hear some noise in the background. Okay, now it's disappearing. The title is of my talk is 2D material-based nanolubricants to achieve green lubrication. So actually, this talk is rather an accumulation of research result I took from the literature, because actually at first I would like to present some of the results I have got now, but due to this pandemic situation now, there is so small thing, so little thing we can do. So the result is still not very good to be presented. But I hope I can point out some important development that has been done to 2D materials to be used as nanolubricants for green lubrication. So my talk will consist of 7 parts. Yeah, the first is about green tribology and then development of additive and carbon-based tribofilms, and then 2D material nanocarbon allotropes, and then about green lubrication and some future research and development. And then the last one is the closing remark. So now let's start about the term of green tribology. So if we have known that tribology comes from a Greek word of tribos, which means rubbing, which is defined as the sign of friction where lubrication of interacting surfaces in relative motion. So this term at first appeared in United Kingdom in 1966 by the founding father of tribology, which is Professor Josh. The term of green tribology is defined by Professor Josh as the science and technology of the tribological aspect of ecological balance and environmental of biological impact. So in order for something of a tribology to be called green, it has to have some balance between the environment and biological impact. And there is one other definition given here by Hill and Kassenbaum, that the green or environmental friendly tribology emphasize those aspects of interacting surfaces in relative motion that are important for energy conservation and conversion with respect to environment sustainability, and which have a major impact on the concurrent environment problem of global warming. So if we talk about green, everything about green is about environment sustainability, about solving problem of global warming, and about energy conservation. And the most important thing is to improve the quality of life. The tribology process, such as wear and friction, lead to loss of material and energy from the interacting surfaces of components in equipment and machinery. So that makes them inefficient and redundant in early stage of life. Then we have frequent replacement of equipment, and it will lead to huge waste of energy and material. And the basic goal in green tribological efforts is to include reduction of material loss, reduction in energy loss, and life cycle extension. Then to achieve the tribological research to improve the energy should achieve the reduction of material and energy loss due to wear, and then the reduction of energy loss due to friction, and conservation of energy and non-renewable resource by extending life, and cycle the components, reduction of elimination of lubricants, reduction or elimination of lubricant by proper selection of low friction mating surface. And there are 3 steps to identify the typical tribology energy sinks in industry to reduce the reduction of tribological losses in major sinks such as utilities and transportation, exploitation of energy conservation potential of new surface modification. Then let's talk about application. We have such as gas fuel cars. And then now with technological development, we have hybrid cars, which are fueled by gas and electricity. And then we have Tesla car, which are fully use the electricity. So we have some energy conservation here. So we have some efforts to reduce the global warming by burning less fuel. Also, we have such things with the locomotive, which are fueled by diesel fuel, to train, bullet trains, which are powered by electricity. But what kind of, what about the ship like this? Are we going to expect some kind of ships that are fueled by other than mineral oil or coal or nuclear? What about aeroplane? Are we going to expect in the future the aeroplane that does not use the mineral oil for fuel? So we don't know. But if we think about this change of energy, like for example here, we have gas or diesel fuel or nuclear, or here like a gas change to electricity, then we have some questions. Where does this electricity come from? Then we see here, according to this graph here, that in 2020, a major part of electricity is produced from coal and natural gas. So what is the point of using electricity car if the electricity we use for the car is produced by the gas? It's just the same. So in the future, we have to think about producing more electricity from renewable resources, so that the electricity we use for electric car or electric train or other application will come not from burning the fossil fuels. So then we have a sustainable world, we have energy reduction, and we have a better environment. Then what is green tribology actually? So in according to Nozonovsky and Busan, the tribological research to improve efficiency in energy should achieve the first, reduction of material and energy loss due to wear, reduction in energy loss due to friction, low wear, low friction, and extending the material life. And then another one is we should reduce or eliminate the lubricants by proper selection of low friction mating surfaces. And in this case, we should modify the surface. If you see this equation here, this is taken from Hutchings' books, that coefficient of friction is shear force divided by hardness. So if you want to reduce the friction, you need to reduce the shear force, which means that you use lubricants, or you can use harder mating surface, increase the hardness. Like for example, you use the coating, you modify the surface, but you don't know which one will work. But we hear and we see and we find out that the friction reduction is caused by the combination of lubricant and lubrication and surface modification. Now let's go to some works to achieve the green tribology. I heard some talk from before this about the polymer brush, and this is called surface modification, or using lubricants. So lubricant to achieve some surface modification. So to achieve green tribology, we need to reduce the material and energy loss by using methods that has minimal impact on environment. So first, we use environment-friendly lubricants. Like we use polymer brush mixed with water or MOS2, or we should modify surface, just like the environment has shown us how the surface is modified to achieve some, like for example, this water here that has low surface energy to this, thanks to this kind of surfaces. So in order to have low friction or low wear, lubricants are used. So why lubricants are very successful? It is because the additive. So we have seen many additives here, and we have seen that that DDP is very successful, and molybdenum friction modifier is also successful. And now we will see that polymer friction modifier and nanoparticle will be used for future additives. So this is the mechanism of additive. So the first one, is polishing mechanism. So the additive will work on the surface and change some surface to have a lower friction. Or the second one, the mechanism is mending mechanism. So some pits that are generated during the friction was filled with the nanoparticles and provide surface self-healing. And then ball bearing mechanism, so it acts like the third body, such as ball bearing. And the fourth one, it is tribofilm formation. So it forms some film on the contact interface that has a low shear force, so that the friction and wear reduce. And this is what people have found out, that like this in such of ZDDP, in the contact interface, a ZDDP tribofilm is formed. And then with molybdenum, also some tribofilm or tribolayer of molybdenum is formed. And this is how the mechanism works. So actually, this layer, this tribolayer, which is formed on the contact interface, with the presence of additive, will form a contact tribofilm which has low shear force, and then it makes easy for the two surfaces to slide each other and resulted in low friction and wear. And now we should think about what is the carbon-based tribofilm. So by using additive, it works by forming some tribofilm, and the tribofilm has low shear stress among them, so it makes the surface slide easily and resulted in low wear and friction. So this kind of principle can be achieved by using or by using the material of carbon like this, graphite or amorphous carbon, which is called diamond-like carbon coating. So if you see this graph here with DLC diamond-like carbon coating, the hardness is very low. It has a high hardness, but it will give a low friction. So by using additive, we can have tribofilm, which sometimes which is in the structure of carbon base, but the carbon-based tribofilm we can also produce by the surface, on the surface, before the friction. And this shows the friction curve of two friction pair. The first one is steel with no coated, and the second one is the DLC coated. And we can see that with DLC coated, the friction has reduced by the factor of 3, from 0.6 to like less than, I think less than 0.1. And this structure of carbon has a lamellar structure like this. So this has a low van der Waals binding force. So it is easily slides among each other. So this is an example of steel lubricated by DLC coating. And we can see here that the sliding, where the worn here occurred between the coating and the mating surface. And in order to find out or study the structure of the coating, we can use the Raman spectroscopy. And this such coating is shown by 2 peaks here in the D band and 1 in the G band here. So this kind of carbon-based tribofilm we can use to coat the surface to have low friction and wear. Then this carbon tribofilm can be deposited on, produced on the contact interface by 3 methods. The first one is by physical vapor or chemical vapor deposition. So we can do some deposition in the chamber, and then we use to apply the surface. And we see here sometimes after the friction test, the coating is still there on the contact interface, but sometimes it worns out, but produce some tribofilm here. Like in this one, it has worn out, but it has produced a tribofilm. And here, the most important thing is not the coating itself, but the transfer film here, because the coating is going to disappear as friction goes on. But the transfer film it produces will keep forming and forming again, and it will help. If we can produce such structure, it will result in low friction and wear. The second one is such tribofilm can be formed on the contact interface by in situ tribochemical process. This example here shows that the oil or the lubricant does not that the contact interface does not coat it by any coating, only use the base oil or formulated oil with some additive. But here we can see that after some friction, some carbon-based tribofilm has been formed on the contact interface. And this is shown by this graph here. That it has peaks in D band and G band. So it can be formed on the contact interface by in situ tribochemical process without coating. And this one also shows that by using the bio oil, I use here, here we use the palm methyl ester, which is derived from crude palm oil, that after the friction, we can find some peaks here on the D band, which shows that this is the carbon-based tribofilm, and this will result, this carbon-based tribofilm was formed on the solid surface as a result of carbon decomposition from the palm methyl ester assisted by tribochemical process. And here, using the methane without coating, some kind of carbon tribofilm can also be produced on the contact interface. The tribochemical conversion of methane to graphene, nano-onion, and disordered carbon at atmospheric pressure and room temperature. So it is possible to produce such carbon-based tribofilm by using in situ tribochemical process. And the third one, we can also produce some kind of carbon, some sort of carbon-based tribofilm on the contact interface using the 2D material. We have many kind of 2D material here, like for example, graphene or HBN or MOS2 or WSE2 or fluorographene. So this structure, carbon structure has two-dimensional. Like for example, here we see these graphene flakes, and these graphene flakes can be used as additive. So this graphene flake can be dispersed in the graphene as graphene solution with some fluids, and then supplied to the contact interface, and then it will form interlayer, which is this tribofilm with transfer graphene nanoflakes. So this two-dimensional structured tribofilm is formed on the contact interface to fill the grooves of the surface and then provide the surface with low friction and wear. And this actually can be, this carbon tribofilm can be delivered to the surface during the friction or in operando using dispersed nanocarbon particle solution as lubricant. So such tribofilm is actually not deposited on the surface, but delivered to the surface using some solution as lubricant. And I will show you some example. Like for example, here from Daicel Corp Japan, they have produced so-called nanodiamonds. So these nanodiamonds can be dispersed in mineral oil. Then here, without the nanodiamond, you see a lot of pit here, a deep pit here, but with the nanodiamond dispersed in mineral oil, the wear is very much reduced. And then the green lubrication. What is the green lubrication? Is to achieve a desired behavior of contact interface using material science and technology with minimum impact on environment. Why I say desired behavior of contact interface? Because sometimes most of the time, we want to reduce the friction. Like for the elements or components in machine or engine. But what about the shoes? Are you going to reduce the friction of your shoes? I don't think so. What about your tire, the car tire? Do you want to reduce the friction of your car tire with the road? I don't think so. But in the case of friction in wear, if you want to reduce, it will involve the process of selecting the lubricants and additives that are safe for environment and biology. And this can be achieved by using nanocarbon allotropes, which is a two-dimensional nanoparticle additive. And the mechanism is that the two-dimensional nanoparticle will be delivered to the contact interface during the friction, and it will produce lamellar tribofilms on the contact surface with low binding energy, which results in low friction and wear. And this has at least two requirements. You will need a fluid which has a good solubility or dispersion stability to the graphene or to the 2D material. Well, you can use it will disperse in mineral oil, but if you want to use the environmental and biological safe solution, maybe you can use the bio oil or vegetable oil. And then you will require a suitable material combination, because sometimes if you find some publication, you will see that some sort of very good tribofilm will be formed on some contact interface using this and that material. But what you have found, you will tell people is that actually you try, and if you get a good result, then you're right. Most of the time when you try, you will have not very good result. So you have to look for suitable material combination that can work with the type of the solution or additive you are using. And here some of the result that graphene can be dispersed in alcohol, and few layer of graphene can be formed on the contact interface. And in this case, small amount of graphene containing ethanol decrease the wear by almost 4 orders of magnitude and friction coefficient by a factor of 6. So its graphene layer as two-dimensional nanomaterial and form a conformal protecting coating on the sliding contact interface. So what you do is you add some graphene in alcohol and you use it for the metal, and you find like this. This one is, this A and B is without the graphene in the solution, and here C and D is with some graphene in the solution, and you can see that the D and G peak appears here, and then E and F, you will have a smaller wear. Then what happens is every 400 cycle, you add some more graphene. So this one is only one, you add once and you use, and this one is with intermittent adding, like after several hundred cycle, you add some more graphene, and then after several hundred cycles, you add some more graphene like this, like that, so that the tribo layer here is produced and then disappear, and with new graphene added, it can be produced again. And the next example is nanocarbon, which is dispersed in water-based emulsion. So here it is shown that the graphene nanoparticle is entrapped in the pit and this shows that this graphene has act as a tribofilm, as a protective film that reduces the wear and coefficient of friction. And here, by only the addition of 0.8 weight percentage, it will result in like 60% of reduction of friction and wear. And this one, it is show that graphene is dispersed in ionic liquid. Yeah, these researchers here use this ionic liquid and achieve lower friction compared to the ionic liquid that has no graphene dispersed. And here, the wear rate of stainless steel can be reduced up to 70% by ionic liquid film, and then 57% by dispersion of graphene in lubrication. So, what is the challenge for the future? You have to find a correct form and types of treatments for nanoparticle. Then you can use, for example, whether it's a flake types or nanotubes, and you need to do some treatment with using the some solution to increase the solubility or stability by using some surfactant maybe, and then you find out some liquid for the solution, and this liquid need to be environment friendly, like for example the ionic liquid or ethanol or bio oil, or why don't use water? Because the idea is to transfer the 2D nanoparticle to the contact interface. So the solution can be anything if it has good solubility and stability. Then you need to use, you need to find the correct friction material combination, because like the liquid, like for example the bio oil, it has a large amount of oxygen, and it will cause corrosive to the material. So in order to find out what is the combination for green lubricants, it is actually the material selection. And then you need to think about what kind of material, what kind of fluid that is suitable to be used. And then you need to think also, can we use the same lubricant for a gas-powered engine car and the full electric engine car? Because this we have combustion and this we have motor. Maybe in his we have 100% contact, and here motor not 100% contact. So can we use the same lubricant for the future? And then also we need to think about the cost. Now the cost for producing nanoparticle is quite very expensive. So that makes the additive of nanodiamond is still quite expensive, but in the future, maybe with the advancement of technology, the cost will decrease. And then, okay, maybe I have finished this talk a little bit early, but I think we should have more time for discussion later. I'd like to give some concluding remark here that green lubrication can be achieved by lubricants using two-dimensional material and environmental fluid, friendly fluid. And research and development are required to find correct material combination. So this is the job of us as a researchers. And the cheap and mass production of two-dimensional material is necessary for cost benefit. And the next one is green lubrication has to be supported by regulation or policy. This is because the green lubricant is expensive. So if you don't have regulation, then nobody is going to use this one, because everybody will ask you whether is it costly or is it cheap. So it needs to be supported by regulation. So for us researchers, what we have to do is to try again. And then I would like to end this session by one quote, that environmental conservation is expensive. If you are using cheap way to get things done now, it means that someone in the future will have to pay for the price balance. So I think this is conclude my talk.
Yeah, thank you
I
very
would like
much,
to
sir.
give
This
back
is
to
Dr. Katiyar from SRM. Yeah, sir. Thank you very much, sir.
Yeah.
Yeah, sir. Are you hearing me?
Yeah. Yes. Very nice and clear.
Yeah, sir. Yeah, sir. Thank you very much, sir. This is
Thank
Dr.
you.
Jitin Katiyar, sir. I'm colleague of Dr. Rao.
Okay. Yeah. Thank you.
Actually, sir, one question came, don't know the name, Del PC is written. Is there the role of crystal structure carbon-based additives on tribological performance of lubricant?
Oh, yeah. Right here, I can read the question. Is that actually what we have by making or by editing additives in lubricant is to produce some tribofilms on the contact interface. And this tribofilm that has a, I mean, that is very nice or give a low friction and wear, always shows that they are having some crystalline structure. They have sp2 and sp3 peaks. That means they are in carbon structure. So this slide, they have low van der Waals binding energy. It slides very easy among each other. I think so.
Sir, next question asked by the Srinivas. He wants to know, carbon-based material is used as a lubricant. Will not it increase the carbon footprint?
Yeah. Well, if you think about that, well, my answer is I don't think so, because you will use a very small amount of carbon, which you use. Actually, you converted one carbon to another form. Like, for example, where do you have this nanographene? You use like carbon from coal or from burning some trees, and then convert it to the graphene. So it actually it's the same material. I don't think it will increase the carbon the carbon footprint.
Okay, I hope
Because
he will
yeah, right.
get the answer. If participants, any questions from your side, you can at least unmute yourself and then ask. Another question asked by Anand Singh Rathore. This all are used very much for low load application, but in high load it is applicable because manufacturing cost is very high.
Yeah, right. In one of my tests, I even used the 1.2 gigapascal load. I think it works for a high load. And one of my colleagues have tried to use it in the piston ring combination. So what he used is he mixed some graphene to the oil, to the fuel, and then actually he took the piston ring and then analyzed that it has formed some graphene layer on the contact interface. So it works in application, I think.
Sir, one question more beside that.
Yes, yes.
Manufacturing cost is very high for this nanoparticles because nowadays science is not up to marks developed that can make that economic way. Have you any alternate solution for minimize the steps of?
Yeah, I think yeah, this is the most problem, because in order to produce a reliable, very uniform graphene, it is very costly. But actually, you can produce it by yourself using electric. You can produce it using your laboratory.
This is the question. It can be prepared in laboratory, but some countries prepared like the Japan, which have the high economy, but rest of country having developing, either developing or undeveloped. What is the solution for that?
Yeah, you can actually, if you want to produce some graphene nanoparticle, you can use electrical exfoliation by yourself. You use some solution and then some electrical devices in your lab, and you can produce some not very costly. But the quality, I don't know, because in some if you have a very nice quality one, if you have a very good quality and you have to buy it from some manufacturer, and it will cost very much. But I think for us, for you, you can use the simple method for mass production with electrical exfoliation. You can have some graphene for yourself for the test, and if you find some good result, and then you can think about how to produce it in a larger scale.
But according to
Yes,
demand.
Another question. Okay,
Yes.
Anand, you can proceed.
No, sir. Please, you, sir. I will later.
Sir, another question asked by the Suraj. Again, he wants to know that we are using sp2 or sp3 carbon, then which crystal structure shows low coefficient of friction, either sp2 or sp3?
I think sp2 and sp3 will appear at the same time for the distorted graphite. So you have sp3 appears for diamond, and sp2 is for graphite. And if you have some graphite, it is distorted, it will appear both peaks, and it's called amorphous carbon. So if you use graphite or graphene, you will have both sp2 and sp3 in the structure.
Sir, in which case the coefficient of friction will be low?
Well, mostly you have you don't produce sp3 because sp3 is diamond. Mostly you will have sp2 is a graphite, and if you the DLC coating itself is amorphous carbon, which means that both sp2 and sp3 appears in the structure. So if you have the lamellar structure of carbon-based coating, if you analyze with Raman, you will have both peak of sp3 and sp2.
So I think, sir, I think sp2 will give the lowest coefficient of friction. I hope, because that is a graphite, and that's why in diamond like coating, both sp2 and sp3 are there, because of that reason it will show the lowest coefficient of friction, because carbon graphite like structure always shows the lowest coefficient of friction rather than others.
I agree to you, sir. I agree with you. Sir,
yeah, sir, another question asked by the Srinivas again. Can you please specify what is the procedure?
Okay. At first, you find some soluble. You check whether the graphene will be soluble to your liquid. Like for example, you try your fluid. Is it dispersed in, like in my experience, the graphene mixed very well with alcohol, ethanol, or with some other solution. And first you put alcohol to the whatever solution you want, like for example for mineral oil, and if it disperses very well, then you add the graphene, and then you can have like mechanical stir, or you can have ultrasonic wash, and you mix there, and then that's all I think. At first you have to check whether it is soluble or not.
Sir, one question from my side.
Yes.
You have discussed about the carbon nanotube and also the graphene. Is there any method for manufacturing the commercial method for the easier way and economical way for the carbon nanotube and graphene?
Well, the best thing I know you can do it by yourself is the electrical exfoliation. You can look for the internet. You have people share the video of how to make graphene by a cheap way.
Okay.
Electrical exfoliation of carbon.
And what about the carbon nanotube?
The carbon nanotube, I don't think we have a cheap way to do that. You have to have something.
Yeah, that's why it is costlier.
Yeah.
There is no cheap way, because graphite and graphene we can produce it. But CNT production is
CNT is
costlier.
no. There's no way of cheap production of CNT.
Yeah,
Okay.
but at least a few milligram also gives a very good lubrication in CNT.
But
Yeah,
sir, like
right.
our developing country like India, there is the demand of the huge amount of demand of the lubricants. So how can we reduce the environmental and eco-friendly and green tribology, because we have to produce lot and millions of tons.
Right, that's the problem. That's why
this is not in practical. That is only theoretical.
Yeah, that's why I say that if we have a green tribology, sustainability, it has to be supported by policy. Without policy, like for example, like let's say Japan, they produce hybrid car. Then the government will subsidize half of the price of this hybrid car so that people can buy. Without that, nothing they can do. Like for example, if you want to use cheap way, we have a nice lubricant now, although it's not very good for the environment. We can do it in a cheap way. But if we want to go sustainable in the future, we have to change this, and this is not cheap. This is costly.
This is the major question, sir. The developing country, either government or peoples, don't understand what is the values of environment. Okay, they are living present, so we are at the laboratory phase, not in the practical phase.
Yeah, right. So
this will take at least 15 and 100 years.
That's the problem. Yeah. I agree with you.
But sir, I hope, sir, so many developments is going on in the sustainability aspects, and maybe in the future we can at least adopt, because slowly we are moving a hydrogen as a fuel. Then slowly we can move to the sustainability aspects also.
Yeah, right. Especially in right now, maybe we have a low fuel price because of the pandemic.
Yeah.
But what happened if the price now is like 100 times more expensive? Then you will actually find or think that, oh, we better use electricity, or we better use other resources. It's a matter of choices, I think. Right now, you have a cheap choice. Why would you use the expensive one? But as I said before, like if we want to think about the sustainability, we have to move. We have to have policy. The government we have to support us. Or why we are talking about sustainable?
Yeah, sir, that's right, sir. Okay, sir. So there is no further questions in that particular session. So thank you very much, sir, for accepting.
Thank you very
our
much for
invitation.
inviting me, and very nice to be able to talk at this. I'm sorry for maybe finishing too soon, but be nice to.
No issue, sir.
talk to you.
It's
Yeah.
a lunch time in India, so
Okay,
all
nice,
are
nice.
also very hungry.
Okay,
So
thank you.
Thank you very much, sir. Thank you, sir, because you accepting the invitation in a very short notice also.
Thank you.
And,
My pleasure.
Also, thank you, sir, and looking forward in future some collaboration in this biolubricant. I'm also
Thank you.
interested to work in this area. So thank you very much, sir. Okay,
Thank
sir.
you.
So dear participants, we will meet again at 2:30 after the lunch. Please come on time so that we will start next session on time at 2:30 p.m. So please be on time. Thank you very much to listen these two sessions. Hope you all enjoy and also learn in this lubricant era, in the nano lubricant or aqueous lubricant and 2D based graphene or graphite based flax lubricant. So thank you very much to all of
Thank
you.
you, sir. Thank you, sir. Thank you for organizing such knowledgeable, fruitful, and wonderful lecture for us. Thank you.
Welcome, welcome. Thank you.
Thank you, sir. Thank you very much.